All right, continuing with number 15. We have a slow sled on some packed snow. There is not, it's not a frictionless situation. And we also have a person sitting on that sled. Okay. This is an example where if we used the sled as the object of our free body diagram, we would have a normal force that was not equal to the force of friction. If I was looking at the sled by itself, I would see in terms of the forces that there is a 46 Newton force of gravity acting downward on this sled. But we would also have this, I'd have to make it very large here, 715 Newton force of the person on the sled. All right, so the person would exert an extra downward force of 715 newtons. We know that we do not get, for any object moving along a surface, we do not have a vertical acceleration there. And so the normal force, as large as that would have to be, we need to cancel that out. The question, though, is about pulling this sled across at a constant speed with some applied force and some resistance due to friction. When I break this up in the vertical, I do not need to pay attention to the applied force or the frictional force. I just have the normal force minus the force of gravity for the sled, also minus the force of the person, equal to mass times acceleration in the vertical. Since I know that my vertical acceleration is 0, I know that the force of gravity on the sled is 46 newtons, and the force of that person is 715. Can pretty quickly determine that the normal force that's acting on that sled is just the combination which is 761 newtons. In the horizontal, just off of the free body diagram alone, I'd see that the applied force minus the force of friction is equal to mass times acceleration. Since it does say at a constant speed, I'll also be able to say that my acceleration is 0. We are trying to find the applied force. At this point, we would recognize that the applied force just has to be equal to the force of friction. The equation for the force of friction is the coefficient times the normal force. So I can see that the applied force is going to just be equal to the 0.11 coefficient of friction times the normal force, which is 761 newtons, giving us a force of 83.7 newtons. So here we have an inclined ramp type problem. Typically, ramps are always described with the angle that the plane of the surface makes with the horizontal direction. So labeling that angle is fairly important. We have our skier, and we want to know what their acceleration is going to be. Well, if we know that our acceleration is going to be down this incline, we want to choose our coordinate system so that this acceleration only falls along one of our axes. So we all inclines up into situations where we have one axis. I can call this the perpendicular axis that's perpendicular to the surface, and I have one axis that runs parallel to the surface of the incline. I can still draw my forces the same way. I have the force of gravity, which acts straight down, the normal force, which acts perpendicular to that surface, and we do see that there is going to be a frictional force, which always acts parallel to the surface. So the only force that actually has to be broken into components that are parallel and perpendicular to the surface are the force of gravity. In the vertical direction, I can see that this component of gravity, given that this is the same 30-degree angle, if Fg is the magnitude of my force of gravity, then Fgy, or Fg perpendicular, is going to be equal to the magnitude of my force of gravity times the cosine of theta, and the only other force in the vertical direction is normal, so I really have normal force minus the component of gravity that is perpendicular to the surface of the ramp equal to ma in the vertical, but we know that our vertical acceleration is 0. I know then that my normal force just has to be equal to this mg cosine theta. So I can go ahead and solve for my normal force. And get 594 newtons. We need to know what the normal force is because in the horizontal, this parallel component of gravity is fighting against this force of friction. And so the parallel component of gravity is going to be mg sine theta. As long as we're talking about the angle that the ramp makes with the horizontal, that will always be the case. In the horizontal direction, I really have Fg parallel minus the force of friction is equal to mass times the acceleration in that direction, which is perpendicular or parallel to the surface. So now I can expand this and I see, well, mg sine theta is going to be 343 newtons. I'm going to subtract my coefficient of friction, but remember the force of friction is equal to mu Fn. That means it's that coefficient times my 594 Newton force. And we still have our mass of 70, and the only thing really left to solve for is our acceleration. This mu is just 0.11, or sorry, in this case it's 0.15. So if I did all these calculations divided by 70, which I'm going to do right now, the final calculation for the acceleration would be 3.6 meters per second squared. Horizontally launched projectiles just utilize free fall motion in the vertical with constant horizontal velocity. So when I look at what's happening in the vertical and the horizontal direction, I can break it into components because I want to use my equations for motion, but they're only good in one dimension. So in the vertical, I know that Vy initial is equal to 0 because the definition of horizontal launch is that there is no vertical component. I also will always have the vertical acceleration is equal to 9.8 meters per second squared. And we also have my vertical displacement. Delta y, my vertical displacement. In this case, I know that my displacement and my acceleration are in the same direction, so I'm just going to choose down to be my positive direction and say the change in my position is 76.3 meters. That's more than enough to solve, because if I'm going to use the equation df di plus vit plus 1/2 at squared, and I apply that in the vertical, I'm going to end up with 76.3 is equal to 0 plus 0t. All I'm going to be left with is 1/2 9.8 t squared. After you rearrange and solve there, you're going to get time is equal to about 3.94 seconds. Once I know how long it's going to be in the air, because we have 0 horizontal acceleration, whether it's a horizontal launch or something launched at an angle, my horizontal displacement is just the product of my initial horizontal velocity and time, because it is constant horizontal velocity. So I take that 3.94 seconds, I multiply that by the 5.8 meters per second, and I would end up with 22.85 meters traveled horizontally before we get to the bottom. If we want to know about the components of velocity, well, then we're going to be looking at the equation that relates velocity to acceleration and time. In this case, well, my horizontal velocity is constant. I don't know who's going to miss that question, but somebody is, and I will have no sympathy for you. In the vertical, I start with an initial velocity of 0. I have my acceleration due to gravity. Actually, I believe there was a discrepancy here on this question where the WebAssign was only accepting negative values because they just unilaterally decided that down was negative for this question. So if you want to get it right, you would have to say negative 9.8 times 3.94 seconds. And so that would give us a downward velocity in this example of 38.612, wherever we want to stop there, meters per second. All right. Let's just think a little bit about these equations for motion. And we want to compare a projectile's motion on the Earth and on the Moon. So we throw an object with the same initial velocity on the Earth and the Moon. How things are going to be different? Well, I think we're assuming that it's launched, right? And we're assuming basically the same launch, just in different places with different accelerations. Well, regardless of what our acceleration, the way that my velocity is broken into components is really going to be the same, right? I'll still have the same horizontal component of velocity because there's no gravity in that relationship, right? Vx, or any vector, well, in this particular vector, if this was at an angle, Vx is equal to V cosine theta. If I chose a different angle, it'd be sine theta, but it's still, there's no gravity there. Now, time of flight is a little bit different because it depends on my vertical component, but it also really depends on my acceleration due to gravity. Since my acceleration due to gravity is smaller, we can even just think about it. Time up, we use that one a lot. It's Vy over g. Well, if g is smaller, time up is going to be larger. Total time is going to be larger. The maximum height we reach, well, if we're going up for a longer period of time, then we're also going to go higher, right? We can go back, but anytime we're even trying to make a comparison of things here, we can still go back and compare it to our equations. So df is equal to di plus vit plus 1/2 ayt squared. Well, you might think, well, we have a smaller acceleration on the moon and a larger time. Maybe it's the same, but the key factor here is that our time is squared. We also could relate this to the equation that doesn't have time, Vf squared equal to Vi squared plus 2a delta d. If we're looking in the vertical, we would, whether we're on the Earth or the Moon, have a final velocity of 0. Either way, we're saying we have the same initial velocity. If our acceleration is in the opposite direction, then we can see how a smaller acceleration would give us, a smaller acceleration due to gravity is going to give us a higher value. And then when we realize that we're in the air for a longer period of time and it's a constant horizontal velocity, it will definitely end up going further because it's in the air for a longer period of time with the same horizontal velocity. For circular motion, whatever direction you're moving, right, our velocity is always tangential, right, perpendicular to the radius, and our acceleration, and this is v, acceleration will have to be directed towards the center. The definition of centripetal is center-seeking, and that just describes the nature of the acceleration. We can't say that the acceleration is north, south, up, down, left, right, because that direction is constantly changing, but it's always towards the center. And we have the equation, our centripetal acceleration is our speed squared divided by the radius. In this example, that would be 9.5 meters per second squared divided by 23 meters. Giving us an acceleration of 3.9 meters per second squared. an acceleration is just an acceleration. It's just a way to describe how something is moving. We still have the application of the second law, which tells us our net force is mass times acceleration. In the case of centripetal acceleration or circular motion, that basically ends up with mv squared over r, but it's just a net force. It describes the relationship between different forces. If I have a runner running around a track, and let's say this track is kind of circular here, well, I might have a normal force on the track and the force of gravity. Those aren't acting towards the center. There's really only one force that can act towards the center, which would be the force of friction. If this runner was on a very slick track, he wouldn't be able to make the turn, or if he was running too fast, he would slide and slip. It's actually the static force of friction that keeps things on the road so that they don't slide out in the mode of kinetic friction. This is another basic horizontal launch problem. We know how high the table is, and we know how far the car goes before it hits the ground. The basic setup is still the same. We know that Vy initial is going to be 0. We can say our acceleration is in the vertical is negative 9.8 meters per second squared. If we want to say down is negative. We don't know what our initial horizontal velocity is. We do know that our horizontal acceleration is 0. We do know what my change in vertical position is. Change in vertical position is negative 1.275 meters. And we know what the change in my horizontal position is. It is 0.4 meters. So again, we divide our horizontal values and our vertical values. And I can say negative 1.275 is equal to initial vertical velocity is 0, so I just end up with 1/2 negative 9.8 times t squared. Rearranging this is going to yield us with time is about 0.5 seconds. If we know how long it falls for, that's also the same distance that we were moving horizontally at this constant speed. Change in horizontal position is equal to Vx initial times t. So that means 0.4 meters is equal to Vx initial times 0.5 seconds. 0.4 divided by 0.5 is going to give us 0.8 meters per second.